Welcome to NanoMatters, the podcast that explores examples of nanotechnology. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Here with me today is David Muller, the Samuel B. Eckert Professor of Engineering in Applied and Engineering Physics at Cornell. He also serves as the co-director of the Kavli Institute at Cornell for Nanoscale Science. So David, you and your colleagues recently published a world record of imaging atoms in an electron microscope. Why is seeing atoms important?
So great to be here. And the simple answer is, the old joke is never trust atoms. They make up everything. And if you want to know what they're doing, well, you got to see them. Most of the modern technology we have, the success or failure of that depends on just a single layer of atoms at the interface between dissimilar materials. So transistors are made up of lots of different materials stuck together, and the thinnest part is just about 5 atoms thick. And if you want to know what's going to happen if it goes wrong, well, you got to look at those 5 atoms. And if there's one out of place, you're in trouble.
What is your new instrument able to do that other microscopes have not been able to do in the past?
The sharpness of an image in every previous microscope has been limited by the instrument itself. How sharp or how blurry that image is set by the microscope. Now we've built an imaging instrument that the resolution is so good, the blurriness that you see in the image is not related to the microscope itself, but to the actual sample we're looking at. So in this case, the width that we see for each atom in our image is because the atom itself has got small thermal vibrations that cause it to wobble around, and that thermal blur is bigger than the blur from the instrument itself. So for the first time, we can actually see in detail how every atom is wobbling and which way the bonds are strong and which way the bonds are soft.
So you said that you can see the vibration of the atom, or that's what gives the blurriness in the images. Can you explain how an electron microscope images atoms at this level?
So an electron microscope uses electrons as waves and then focuses those waves down to a small spot. And if that spot is smaller than the atom, when I scan it around, you're going to get a change in recorded signal. Now, what we're doing here is a little more complicated and it requires somewhat more sophisticated detectors. But imagine that my atom is a person and I'm throwing dodgeballs at them. If I throw a dodgeball and it goes whizzing past them and it misses them, it'll travel in a straight line. But when it hits them, it'll scatter off to the side. So if I look at the angle that the dodgeballs bounce off, I can tell not only where the person is, but something about what their shape might be. And we're doing the same thing with electrons. And we had to build a detector that could collect all of these electrons that are scattering at different angles and do it for a huge range of intensities and do it very, very quickly.
So what do you think this advancement in being able to image at this scale will enable in the future?
The key thing is we can see every atom column. And now we know where the atoms are. We can actually look closely enough at them. Like, as I said, you can see them jiggling around. And the atoms that are strongly bonded, well, they don't get to move too much. And the ones that are weakly bonded, they get to rattle around quite a bit. And so I can see what direction the bonds are strong, what direction the bonds are weak. If I'm looking at a turbine blade or a metal, and I can see the atoms where the grains of the metal join together, I can see, is it going to stick together or is it going to fall apart? If I'm looking at catalysts, the catalysts are often little tiny nanoparticles, just 10 to 50 atoms across. And the catalyst works by taking atoms that you're feeding to it, or molecules you're feeding to it, and breaking them apart, and then releasing them again. And I can now look at these kind of reactions and see where things are stuck strongly and where things are not so strong. And for a catalyst, you want things to be not so strong.
So for people who are not familiar with electron microscopy, can you give a little bit of a sense of the scale that we're talking about?
Electron microscopes are much bigger than the optical microscope you would have played with in high school. They tend to take up a whole room. It's almost like the smaller the thing you want to look at, the bigger you have to make things. It has at the top of the machine a high voltage cable coming in to provide the bias to accelerate the electrons. It looks like a little bit of a power line. The electron lenses are electromagnets, and those are pretty big and heavy. And so you've now got a room filled with equipment. You're trying to keep everything stable to well under an atom, right? If it wobbled by an atom, I wouldn't be able to see them. And so the rooms have to be incredibly stable and incredibly quiet. If you talk in the room, the image of the atoms will disappear. The rooms have to be so quiet, we have to slow down the airflow. And in fact, one of our early innovations was hanging a piece of toilet paper that was a foot long, 1/4 inch wide, and single ply. And if that deflected more than an inch, you had too much air movement to image atoms.
So can you compare a microscope to perhaps a telescope, looking big instead of small?
Right. So that's actually a good comparison because, even though microscopes are used for looking into very small things and telescopes are used for looking out for very big things, the angular magnification that you need is about the same. So the normal electron microscope, this room-sized piece of equipment, has about the same angular magnification and the same precision as the Hubble telescope after it was fixed up. There was a lovely picture of the black hole in M87, that round orange donut, and people immediately started comparing it to our images because we had orange atoms as well. They're about comparable scale of angular magnification. Our instrument is probably a factor of 10 more precise than the Hubble telescope, given its improvements over previous generations of electron microscopes. So it may well be the most precise measurement imaging instrument we have.
So I recently talked to a high school teacher who his students listened to this podcast series, and he encouraged me to always ask the question, do you have any advice for students?
If you're interested in physics and nanotechnology, get as much math as you can as early as you can. A lot of the things we need to build on that math. And if you've got a lot of practice and experience with that, then it's much easier to build. And it's the language that you speak science in. And if you don't speak the language, it's a lot harder to learn the story that we're trying to tell.
So are there applications in biology and medicine that would use this technique?
So we think it would actually be very useful for imaging biological samples, whole cells in particular, that electrons being high-energy particles are actually quite damaging. So in biological electron microscopy, which is called cryo-EM because we have to freeze everything, the sample is very easily damaged by the electron beam. And so your resolution is set by actually the dose, how many electrons you can put on the sample. And our imaging method collects and uses every electron that goes through the sample. So it should be more efficient and should give us a better use of our electron budget for imaging. And so for the same number of electrons in, which is the same amount of damage, we should be able to get better resolution. And so that certainly is one of the things we're going to be trying in the future.
David, thank you so much again for being with us today. Do you have any closing thoughts that you'd like to share with our listeners?
Now that we've built this tool, we're actually looking forward to having a lot of fun with it because a lot of the fun in science is the unexpected discoveries that you make. And the most fun ones are the ones where you're looking at something and you get to say, not, Eureka, I found this thing I was looking for, but it's more those, well, that's interesting. It's the unexpected questions that pop up and the new things that you get to see, which are the questions you never thought to ask, but that nature tells you, because in many cases, nature is much smarter and more inventive than we are.